Welcome back to another Daishinfinity video. In this video, we're going to prove the induction over odd numbers. So this summation formula, where k goes from 1 to n of 2k minus 1, is just the summation of all odd numbers going from 1 to n. Well, n in the case 2n minus 1, which is an odd number, since 2n is not an odd number. Now this states that the sum is actually equal to n squared, and I would like to prove this to you guys by using induction. So before we dive right in, we have to check for a few k's. So let's say k naught. So let's start a k naught equal to 1, and then let's just plug it in. So it will be k equal to k naught of 2k minus 1, so it's just 2 times 1 minus 1, which is equal to 1, and that should be the first number, so it's actually correct. Let's try for k equal to 2. Then the sum where k goes from 2 to, I'm sorry, I wanted to say n is equal to 2. Then k goes from 1 to 2 of 2k minus 1. Well, we know that the sum of the odd numbers of the two first odd numbers should be 1 plus 3, so 4. So let's just see. This should be equal to n squared. So 2 squared, which is 4. So we can try this for many other stuff. Let k go from 1 to 3, so n is equal to 3. So this should be equal to n, so 3 squared or 9. Let's just check it. 1 plus 3 plus 5, which is 9. Okay. So we want to prove it by using something called induction. So with if n is equal to n, okay, then it should work for n plus 1. Okay, and we just saw that it works for n is bigger or equal to 1. So we want to prove that it's also equal for any n plus 1 element of the natural number. So let's assume that the sum where k goes from 1 to n of 2k minus 1 is just equal to n squared. Let's just assume it. And then we're just going to say, okay, I want to sum it up until n plus 1. So this should be equal to the sum where k goes from 1 to n of 2k minus 1 plus the n plus 1 term. So k goes from n plus 1 to n plus 1 of 2k minus 1. So here we're just going to plug in the n plus 1, and this one should be equal to n squared because this is what we just said. Let's just assume that it's n squared. And since this is the same thing as n squared, but we are just going to plug in the n plus 1 into the n, this should be equal to n plus 1 squared. And this is equal to n squared plus 2 times n plus 1 minus 1. Now what is n plus 1 squared? Any binomial theorem a plus b squared should be equal to a squared plus 2ab plus b squared, which means we can state this as n squared plus 2n plus 1 is equal to n squared plus 2n plus 2 minus 1. So the n squares will cancel out, the 2n's will cancel out for every n, and 2 minus 1 is equal to 1, which will also cancel out with the 1 on the other side. So at the end, we will have 0 is equal to 0, which means for any n, this is proven. Which means that at the end, we can say that for k going from 1 to n of 2k minus 1 is just equal to n squared. Now, we can also think this as a geometric way, Just try to imagine this is a block of where n is equal to 1, so this is the 1. And then we just add the 3. Okay. And so on. So we just add the 5 and so on. 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5, 6, 7. Now what you can do with it is we can just write this as 1, 3, 5, 7. Is we can make it in a way such that you will have a square at the end. Now what is n? N is 4 in this case, since we are summing up 4 numbers, odd numbers. So we should have a side length of 4. 1, 2, 3, 4. And this should be kind of a way to do. So the gap, which is this and this can go here, and this can go here. Then we have n squared. Now how can we do it for any number? So let's say we have 1, we have 3, we have 5, we have 7, and so on. So we have any 2k minus 1. Okay. Now for any n, if we sum up n as so n of those terms, then we need n kind of centimeters. Let's say this is n and this is n, so that it will be n squared. Okay, and some of them will pop out, so we need to put them back inside. And it turns out that geometrically the part that is outside is just equal to half of this. Okay, so the geometric way of proving this is also very important and very interesting, but the classical way is to do it with induction. That's why I told you how to do it with induction, but it's also very interesting. Well, I hope I've proven this formula with induction, and I hope you really like this video. Please like and subscribe, and we'll see us definitely in the next Daishinfinity video. See ya.